I think we would all agree that that was a rich and powerful first session. So Francesco set the scene with that introduction to quantum computing, which really opened all of our eyes. And then Steve, Johanna, and Patrick have brought to life three very diverse areas which employ different mathematical techniques. So I also want to thank the audience because I can see several questions and comments coming in, but please do keep them coming. And we now have 35 minutes for a panel discussion. So just if all the panelists want to feel free to get ready, put on your cameras and be ready to participate. I think I will start with a question that's come from the floor. A question from Livingston Kamoja, who is in Uganda. And he's asked whether in the use of quantum modeling, would we be able to develop a sustainable vaccine development systems that could help actually predict the coming of future pandemics so that we might actually be able to mitigate them and work out which vaccines we should be developing before we're actually in that crisis situation?
Yeah, that is the hope, but it will take a few years. Yeah, in order to really solve those problems, we will need 10,000, if not 100,000, of logical qubits. Yeah. At the moment, we have 48. It's a few days. Yeah. So, on paper, we know that some of these quantum algorithms on these universal quantum computers will give us exponential speed ups for certain classes of problems. Yeah? And some of the problems that I indicated fall in that category, but we don't have the hardware yet. Yeah. So we shouldn't be too optimistic that we will solve the problem tomorrow. Yeah. I'm pretty confident that we will get there. Yeah. But it will take a few PhD generations before we can really address those problems. Yeah.
But I think what you've done is you
solve
sort of
those problems. We can address them now, yeah, but we can solve them. Probably will take a little while. Yeah.
And you've truly opened our eyes to what might be possible. I don't know if any of the other panelists would like to sort of pick up on that point. Or maybe I will bring in Patrick at this point. You've talked about the use of drone technology and looking at the crops and all of that very rich data that can be collected efficiently and so forth. So when we're thinking about pandemics and sort of vectors and diseases, is there a way that we could bring drone technology to look, for example, malaria breeding sites, malaria control programs, and actually get some of that information in order to predict?
So, to my knowledge, I think we even had malaria in Germany after the Second World War, and there's still a region in the southwest of Germany, in the Rhine Valley, where they still suffer a lot from mosquitoes. It's basically not malaria is not the problem, but there are a lot of mosquitoes. And what I understand is that people are using remote sensing data to spot the plots where a lot of water is accumulated. And then they use this for directly spraying, basically using insecticides in order to kill the mosquitoes which are available in these areas. And what we're focusing on, what we're looking at the moment, at least in Germany, is we're trying to reduce the amount of basically insecticides, herbicides, and any chemicals, because it has got a bad relevance for the environment. And I think this can help to basically support using only as much as we need in order to kill basically the nests where the mosquitoes develop. So that would be basically a very good possibility.
Thank you. And I'm not sure if everybody knew that there had been malaria in Germany as recently as that. So that is quite eye-opening. And obviously, Steve, you spoke quite a lot about malaria and looking at particularly these understudied populations. I would be interested to know, Steve, from your perspective, how thinking about these bigger computing models, how can we draw information from many populations? Because I think we all have a tendency to work in silos, whether that be a specific disease or even within malaria, people tend to work in Asia or in Africa or in a different region, and they tend to work in children or pregnancy or, so what could be the future of these increased computational power to really understand malaria worldwide?
I think there's a great opportunity for linking in a couple of different ways. And as I was listening to Patrick's talk, it was reminding me of, this really interesting result that happened as part of the global campaign to eradicate polio, right? When the polio eradicators were walking up into the northern Nigerian area that wasn't very well populated and subsequently not very well mapped, they found villages. They look on their maps. This isn't supposed to be here. Right. And so, but nonetheless, here's a village. They've never been vaccinated because people never even knew they were there. So they go and they vaccinate them, and they geocoded where that village was. And then one of the things they did is they went back to the satellite images and they looked at satellite pictures to say, what are the picture characteristics, right? The phenotype, if you will, of a place where people live. And then they took those characteristics and looked in other places in Nigeria. And guess what? Oh, here's another village. Oh, there's another village, right? And so one of the things that I can see easily happening in the disease space with malaria, with dengue, with, particularly with mosquito transmitted diseases, is understanding the characteristics, as Patrick mentioned, the water content, the foliage, a whole number of different parameters that you could map to say, here's a place where there's likely going to be a lot of malaria transmission because of the characteristics. And essentially you make correlations between here's places we know there's malaria and they look like this. Where are other places that look like that? And then how does that help us granulate out our population models? So then if we can get some really fine granularity, down to the pixel level of knowing what the risk of disease is, it might help then an area say, okay, we think we might have this much malaria. What can we do to actually eliminate it or eradicate it?
Wow, I mean, it's fascinating, and it's fascinating how we can draw between disciplines as well. So when you're referring to polio, because I'm very aware that another silo can be according to disease conditions, and we will soon segue to Johanna and look at some of the other conditions that we might be looking at. A question from Bernd Rosenkrantz is that, to our knowledge, that is those of us on the panel, is there any platform that connects related research fields, for example, agriculture with climate change, with epidemiology? So is there any platform that's doing all of this at the moment, or is that our task to design one? So I'm taking the silence.
I mean, I know there are efforts to bring together climate change and health issues, like there are big efforts in that direction. Yeah, to bring in also agriculture is probably, and there are probably big efforts to bring together climate change and agriculture. Yeah, the next step is of course to bring them all together. Yeah, but the complexity increases exponentially. Yeah, but we'll get there. Yeah.
Yeah, I heard
Please.
Steve's presentation with interest, that it's not entirely unconnected to my field, but I think a little bit of I had an opportunity one time to develop a health economic model where the underlying disease model was driven by the difference between the PK/PD profile of the drugs. So it's not usual to simulate a disease model at such detail for these kind of purposes, because we need to model the patient's whole lifetime. So this is associated with enough uncertainties. But yeah, so there is a little bit of a cross between Steve's field and my field in this case.
Wonderful. And perhaps, Johanna, whilst you have the mic, there's another question that's come through that I think your presentation was really beautiful and simple and clear. And as I remarked, I feel it maybe made it sound easier than it actually is, because some of the decisions are complex. So when you are making decisions of the implementation of control interventions, apart from the cost effectiveness, are there possibilities of considering impacts of those intervention strategies before making the decisions?
So just to be clear that in my job, I would not be making the decisions. So it is rather up to the government, to national health services and so on to make those decisions of what they would like to fund. And the decisions can, for the same analysis, the decisions can be very different in different geographies. So my job would be to make those analyses and to present the evidence in an as objective way as possible. But yeah, so can you just repeat the last part of the question?
So I think it was really thinking about the overall impact of an intervention, almost perhaps trying to do some further modeling, maybe not just of the cost effectiveness to that individual in terms of their qualities, but actually in terms of like future population health, is how I read the question.
Yeah. I mean, there's different, so this is one standard way of modeling, but it is not the only way of modeling. So there could be other types of models developed, but there can also be a lot of other considerations that go into decision making for funding of a drug. So it is, there's a lot of recent thinking around how do we value medicines, like cost per quality is not everything, and there's other aspects such as equality, like if a product is improving some, let's say, underserved population more than population that is already served quite well, should we be funding that rather than something that's already populations well served, but you may have a very good cost per quality. So there's certainly many other considerations as well as the cost per quality. It can be modeling, but it can also be just thinking around what is value to population.
Fantastic. Yeah, I mean, I think there's very complex decisions, and some diseases are more prevalent, but also I think I worry sometimes, as Steve had discussed, some of these perhaps understudied groups who might seem minorities and perhaps might not seem of such great value, but obviously at a human level, they are of immense value.
Yeah, I mean,
I'm wondering whether...
I think, you know, one thing that's interesting is to think about as you start to put some of these different models together, right? The ability to do the what if experiments, the things that are very difficult to conduct in the real world, but very easy to do in the computational world, right? To be able to say, okay, so Johanna's team has identified a couple of parameters that really have an impact on improving quality. So suppose we can then make a drug with twice the duration at half the dose and a third of the cost. What would that potentially do from a benefit standpoint? And that then helps developers target, these are the characteristics that I need in a new generation medicine if I'm going to bring something forward, because anything that does less than that is perhaps not even valuable or worth the effort. So I think that's where a lot of this cross-fertilization can help in those what-if experiments, where modeling, again, can give you a sense of the magnitude, right, of the impact that could happen if you made changes in key parameters.
Mm-hmm.
And obviously, as we often say with all models, that garbage in, garbage out. And so the more accurate inputs to what we might predict from the other disciplines enrich the models. You're laughing, but it is true. I can see some hands raised. First Patrick and then Miriam.
Yeah, I just noticed that there's quite a lot of connections between the talks we just had, because I saw, Steve, that you said something about malnutrition and the validity or the effectiveness of drugs. And I think nutrition is somewhat related to agriculture, isn't it? Right. And at the same time, it's probably not only the quantity of nourishment, but it's also the quality. And I think that the beautiful thing we have with machine learning at the moment there's nothing which stops us from putting all kinds of data from different silos, which are now divided, because we didn't know that we're working on stuff like that, that we could use climate data and satellite data and drug consumption and illnesses and agricultural production, just put that into a model and try to predict things and to see whether we can get better with that using data from different fields. I think that would be a very interesting approach.
Thank you. Absolutely. Miriam.
Thank you. I just wanted to make one comment on the question regarding using modeling to predict future pandemics, and maybe not from a quantum perspective, but I think this is one area where epidemiological models to come in, where we are able to design surveillance systems that can detect early signs of potential outbreaks. And by analyzing the historical data and monitoring key indicators, we can be able to identify unusual patterns. So there is already that existing capacity within epidemiological modeling, maybe not from a quantum perspective, which is not my area, but I just wanted to add that comment.
Thank you, Miriam. I also note that we're joined by Georg Fulner, who is going to be presenting after the break. But by way of brief introduction, Georg is an expert on climate change modeling and all the complexities there. And of course, climate affects crops, it affects disease vectors, it affects human health, it affects poverty, it affects all of this. So Georg, I'm sure you're listening to this with interest and have quite a few reflections on what's been said so far.
Yes, indeed. Good morning, everyone. Yes, I was thinking along those lines as well. Of course, if you think of agricultural yields and how they will evolve in the future in a warming world, right? This is a hot research question, and as Francesco has pointed out, there is this connection between climate change and agriculture made. And as you just said, Catriona, that the health effects are obvious, both from heat waves, but also from changes in vector-based diseases, right? So this is all really relevant to connect all these fields, and indeed, climate change is in a way a nexus between these, and particularly looking into the future. Also, Joanna, your point about decisions which are not made by the scientists, obviously, and maybe, you know, it's good that it is the way it is, but that's also maybe something we could reflect on at some point, right? That we provide some input for decision making, and I'm sure we'll take this up later on, based on models which are great, but have also, you know, some issues. And what does that actually mean if we, you know, how to communicate that, and, you know, what does that mean if we make some decisions based on models which are, you know, great but not perfect, obviously.
Thank you. Miriam, you briefly turned on your camera, then turned it off. Did you have a response to what Georg was saying from the perspective of epidemiology? No, okay, that's fine. So, Francesco, you seem to be the man with the computational power. And at some point you mentioned that quantum computing is not yet effective enough for these kind of like massive amounts of data that might be coming from all avenues, but might be used on smaller problems. So does that mean that the power of quantum computing is being able to solve perhaps models that were previously very computationally heavy? Does it make those techniques more accessible? Or where do we start to move from what we've all been doing to start using some of this technology that you've got in your hand?
You know, as I mentioned, the reason why at this moment, quantum computers are not so good for big data problems is just that it costs too much time to input our normal classical data into a quantum computer. The problem is you need to encode the data sets into quantum states, and that is at the moment a fairly slow procedure. In fact, I think it's probably factor 10,000 slower than to input data in a GPU, for instance. So so even if the computation is faster, you lose time by inputting the data and extracting them at the end. Yeah, so that's at the moment it's not particularly winning strategy. Yeah. On the contrary, if you have problems that don't require large inputs of data, yeah, where you just have a few parameters to run a simulation, yeah, for instance, in quantum chemistry, yeah, there you can already see that quantum computers are already applied with fairly good success, yeah, and the hope is that that will scale up fairly quickly also to application to the development of new pharmaceutical. Yeah, that's essentially also quantum chemistry. Yeah, it's just that the molecules maybe in some cases becomes a little bit bigger. Yeah, but we are slowly getting there. Yeah, that is a reachable goal. Yeah, the other is of course is a similar application, the development of new materials. Yeah. That's also modeling of quantum phenomena, yeah, maybe in a more condensed meta phase, yeah, instead of just in a more chemistry setup, yeah. So those are typical applications where already quantum computers are used fairly successfully, yeah. And hopefully, at some stage, we will solve the problem is not a principal problem. Yeah, it's mainly an engineering problem. Yeah, the first mainframe computers in the 40s, yeah, filled vast halls. Yeah. And your phone now is probably 1,000,000 times faster now than they used to be. Yeah. And quantum computers are now where the mainframes were in the 50s. Yeah. So give it some time and we will get there. Yeah.
So I wonder if any of the panelists have any questions to come back on that about, almost where we would start. We noted that there was quite an emphasis on like sustainability and decision making through your slides, and how this might affect policy making. Where would we start to move? I mean, maybe my panelists are already doing this. Maybe I speak for myself when I say this area of quantum computing is fairly new. But where would we start?
Can I?
Please, please.
There is an obvious start, yeah, and that is to make these new technologies as accessible as possible to everyone. Yeah. New technology are always very expensive and end up being the playground of an exclusive set of people. Yeah, mainly those that build the machines and those that can afford them. Yeah. So what is really important is to start now thinking about how do we make these new technologies that will come sooner or later, yeah, accessible to everybody. Yeah. And there are efforts, for instance, in Geneva, there is an organization called GESDA, the Geneva Science and Diplomacy Anticipator, and they are working very hard to set up an open quantum institute, yeah, an institute where that will be able, through support from various players, to give open access to everyone, yeah, that wants to use quantum computers for a noble cause. Yeah, we don't want to give them access to people that have maybe not so noble causes in mind. Yeah, and there are some of those. Yeah, unfortunately, like for all technologies. Yeah, even with a butter knife, you can kill someone if you have to. Yeah, so we need to be careful and. But it's really important that we start training people, that we start developing the skills, that we make people aware of the opportunities, yeah, so that not half of the world is caught by surprise, yeah, when all of a sudden quantum computers can crack RSA codes, yeah, and the security of of everybody collapses overnight, yeah. And and that is I didn't have the time to mention it in my talk. That is a problem that is already now here, yeah, because if you want to keep secrets for a long time, yeah, you need to think that it's very easy to tap into fiber networks and to download encrypted data. Yeah, everybody can do it if one wants so. Yeah. and I can just store them. And when I have the capability, I start reading all your secrets. Yeah. So the problem is already here now. Yeah. So one needs already now start thinking how to protect information from attacks in the near future from quantum computers. Yeah. In particular, if you're a government or some other agency that stores sensitive information for long term. Yeah. The challenge is already here now. Yeah. So you need to start thinking, yeah. And there are strategies to mitigate that. But that as well requires that we train people, that we create awareness, that we start thinking about it, yeah, so that we are not caught by surprise.
Wow. I mean, you raised some very, very excellent points there. And I would like to pick up on that point you meant about making things accessible and getting the tools into the hands of those who need them. Because very often, and as I've already mentioned, many of our delegates on the call today are from countries across Africa. We have many strong data science communities and also the Pharmacometrics Africa network. We often feel we can lag behind our counterparts in high-income countries. Is there any reason why this technology could not be used in Africa at quite an early stage? I mean, would it be possible to partner, or are the concerns about security and government structures such that it makes it difficult, or a bit of both?
There is no reason why in Africa we can't do it. Yeah? We can probably even do it better if we apply our minds. Yeah? There is no reason. Yeah, we just need to all pull together and make sure that we have access to these things. Yeah? You know, at the end of the day, it's all a matter of funding. Yeah, if our governments give us enough funding to build our own quantum computers, we will be able to do so. Yeah.
And another question, and again, maybe bringing in Georg with the climate perspective, but one of the attendees has asked about things like electricity and sort of impact on environment and climate of these sort of novel techniques. Are there considerations there, or is this actually an improvement on this current situation?
I'm not sure what the question about electricity was, but you know, electricity is more of a first industrial revolution problem, yeah, because you need steam. So
I know, but
a fourth industrial revolution problem. Yeah? But you know, computational tool, classical quantum can help optimize the production of electricity, the distribution of electricity, and all those kind of things. Yeah? That's fairly straightforward. Yeah. The one challenge that you mentioned in passing, yeah, that we have in Africa, yeah, that of course we can use all the tools of artificial intelligence, ChatGPT, transformers, blah, 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 yeah. But our challenge is that we don't have enough data, yeah. You know, we haven't collected enough data to use those, those tools, yeah. And it doesn't help us if we can apply the most fancy machine learning tools if we don't have data to train them. Yeah, you know, one big problem is that, for instance, ChatGPT and all those kind of things, they work very well if you speak English. Yeah. But if you speak one of the many hundreds of African languages and dialects, it won't go very far because it has been trained on that. Yeah. So we need also to be proactive, yeah, and start collecting those data. Yeah, make sure that we can train the artificial intelligence, classical or quantum, doesn't really matter. Yeah, so that we can use them. Yeah. Otherwise, it's very challenging. Yeah.
Thank you, Georg.
Yeah, I was just wanted to come back to your question, Katriona, about electricity use and modeling, and that is a concern, of course, right? And if any of the new technologies can help reduce that, that's of course helpful. But what we're seeing at the moment is rather the opposite, right? The cloud-based services and so on, they all take up enormous amounts of electricity. And even looking at scientific modeling, this is a concern, obviously, right? In particular, coming for someone coming from a climate science institute, right? I mean, we run our own in-house high-performance computing system, and we try to make it as efficient as possible. We run it with renewable energy. We're installing a new one, which is a factor of 5 more powerful, but only a factor of 2 more in the consumption of electricity. But you know, the amounts of electricity used are enormous. I mean, in fact, we are heating our office buildings, right, with the waste heat from this computer, which is a nice, you know, way of using that amount of power. But obviously, it's a concern. And thinking ahead, switching to an energy system which is based on renewables, we also have to think about, you know, efficiently using our electrical energy, and the increasing demands from the new technologies are obviously something we will have to be looking at in the future.
I don't know if anybody has something to come back to on that, or anything we've covered so far. I mean, I think the theme that's coming across to me here when we talk about security, when we talk about environmental impact, when we talk about accessibility and sustainability, is that with every advance, we have to be already working on those mitigations, working on things like data quality as well. I noticed that Patrick, you had spoken about one of the problems being actually the quality of the data. And I was wondering whether perhaps anybody, but particularly Patrick, do you have any insights onto how data quality could be improved, or what research is needed in the next few years, particularly in your sector, but maybe applying to all of us, in using the drone technology, for example, so that we can be confident of the data going in?
Yes, an interesting thing we are looking at the moment is weather stations. So in a project we've developed a low-cost weather station. We basically took components from the internet to make weather stations as cheap as 250 euros. We set up the weather stations with a very small distance from one another. And we found out that we've got unexpectedly a very high variability of rain, temperature, air humidity. And many of the models we are using at the moment in order to say whether we need to do something, whether we need to apply chemicals or not, are based on weather data. And what happens quite a lot at the moment is that people are using very good models, but they're using the data from a weather station which is 10 kilometers apart. And then they say the models are bad. And then I always say it's not the models that are bad, the input data you're using is bad, right? So I think we've got a good chance, especially with all the IoT technology we've got at the moment, to produce more data, which is on a lower scale. The question is that data better? Probably not. It will not be as accurate as a professional weather station. And I think we always have a trade-off between spatial resolution and accuracy of data, right? We can't have everything at the same time. I think, Johanna, you've introduced this ESAR, right? We can take expensive weather stations and use many of them, but that's going to be pretty expensive. And that would be interesting to find out the economics when it comes to this point. And when it comes to remote sensing and satellite data, I tend to ask children questions. And just recently, last year, I asked my students to fly over the same field in the morning, before noon, afternoon, and in the evening. And we compared the resulting drone images, and there was a substantial difference, right? And that should not be, or we need to be aware of that. And there was also a question in the chat, and I think I can relate to that. It's only spectral information which we're getting from images, may it be satellite images or drone images. And if that spectral information does not substantially reflect the difference in yield or in certain pathogens, then the models won't work. Right? It's as simple as that.
Thank you. We're actually enjoying that question about asking children questions and asking them what they think as well, because through all of this, we need to have, a lot of this is about improving the world for our children and bringing the technologies that they will be growing up with. I particularly like the metaphor of well, not metaphor, reality of where we were with cluster computing and original computing back in the 1940s and 50s, and how far we've come. And even a young person like myself, my children don't believe that we did various degrees without any access to internet and things like that. But what will the future be? And I think the future we know is exciting. The future is cross-disciplinary. The future has broken silos, but the future also needs one eye or both eyes firmly on security and risks and risk mitigation. I'm also aware of that classic quadrant, the Johari window, where we have the things that we know, but there are the unknown unknowns. There are things that we simply do not know. And by talking to people outside of our sector, I think we might actually be able to predict and identify risks that we haven't considered with the tunnel vision. So I can see more comments and questions coming, but I believe we are running out of time for this final wrap up of the first panel discussion. And it's now time for me to really thank all my speakers and panelists. As already mentioned at the start by Rohan, we have speakers from all over the world representing many different time zones. We are all filled with passion about this area, and I'm confident we could speak for 24 hours if we had the opportunity. But today we're not going to do that, and I'm going to hand back to Rohan to conclude this session.